Hello, I'm Bretton, one of our MCAT tutors here at Inspira Advantage, where we help students get into medical school and other professional programs. Hello, future doctors. Today we'll be diving into the fascinating world of nuclear reactions. These reactions hold the key to how stars shine and the fundamental transformations that drive reactions at its core. Even more importantly for you, these are incredibly high yield on the Chem Phys section. So let's dive on into it. First, let's discuss fusion. This is the process where small nuclei combine to form larger ones. So we have a 1 gram plus a 1 gram particle forming a 1.98 gram particle. And of course, these are way smaller than a gram, but for easy math, we're going to say it's a gram particle. You might notice that this isn't 2. Well, where did that 2 go? We can plug it right on into the E equals mc squared formula to see why fusion produces so much energy. It's a small loss of mass that is directly converted into huge amounts of energy powering the sun. Fission, on the other hand, is kind of the opposite of fusion. In fission, a large nucleus, typically uranium or plutonium, will split into smaller nuclei, often releasing several neutrons in the process. This process also releases a substantial amount of energy and is used in nuclear power plants and atomic bombs. So now that we've kind of laid the foundation that you need for the MCAT, let's talk about the actual high yield stuff on there. The different types of radioactive decay. Now, you do need to know every part of what I'm about to talk about. You need to know the names and what is changing. Luckily, to help you with this, I've colored what is important for each type of decay, so that'll help you better make your Anki cards to remember this longer. Let's begin with the first type of radioactive decay that you need to know, which is alpha decay. In alpha decay, the nucleus is emitting what's called an alpha particle, which consists of 2 protons and 2 neutrons. This is essentially a helium nucleus, so just think of it as losing a helium atom. This process will decrease the atomic number by 2, so we're losing 2 protons, and we're losing the atomic mass by 4. So again, this can be shown by just drawing the alpha symbol, or alpha 42, explicitly writing this out, and it's also the same thing as a helium nucleus, just no electrons there. Next up, we have beta negative decay in blue here. This is when a neutron in the nucleus is converted into a proton, an electron, and an antineutrino. The electron, called a beta particle, is emitted and the atomic number will increase by 1. So the total mass is increasing by 1. So because we have this neutron essentially turning into a proton, the atomic mass isn't going to change because a neutron and proton weigh basically the same. The only difference in the weight is an electron, and we know that an electron essentially has a mass of 0. So where's that electron going? That is the beta negative leaving. Now, this isn't to be confused with beta positive decay, also known as positron emission. This is the reverse process of beta negative decay. In beta positive, a proton is converted into a neutron, a positron, and a neutrino. Here, the atomic number is going to decrease by 1, because again, we want to think about this, right? We are losing a positron, and this is basically an electron, but positively charged positron. And then one of the easiest ones to understand for the MCAT, in my opinion, is gamma decay. Gamma decay is involving the emission of gamma rays, which are high energy photon. This process usually occurs following other forms of decay, such as the excited nucleus moves to a lower energy state. The reason I think this one's the easiest to recognize on the MCAT is there's always going to be an asterisk here, and there's never an asterisk on any of the others, because it's just the exact sort of same molecule, except it's in an unstable high energy state. Thus, that's what the asterisk means. It just means we're unstable in high energy. So we're just coming from asterisk X to regular X with the emission of a gamma particle. And finally, we have electron capture, which is the process in which an electron from an atom's inner shell is absorbed into the nucleus, combining with a proton to form a neutron and neutrino. And this is going to result in the atomic number decreasing by 1. Another key concept when we're talking about fusion and fission is the half-life of a radioactive substance. This is the time required for half of a sample of radioactive nuclei to decay. And this is an exponential decay process, meaning that the rate of decay is proportional to the number of radioactive atoms remaining in the sample. So can we put an equation to that? We sure can. It's n equals n naught times e to the lambda t. And what are these? Well, n is just the number of undecayed nuclei, n naught is the amount of undecayed nuclei at time 0, and the lambda here is just the known decayed constant. So that can be experimentally derived. Nuclear reactions from fusion and fission to the various forms of radioactive decay are fundamental to the workings of the universe and for the Chem Phys section of the MCAT. So thank you so much for watching this video on decay, and I will see you next time.